We're going to look at graphing some basic log functions here. I call these parent functions because these are log functions with no transformations. These are meant to be starting functions for if you're going to do transformations. So let me explain this here. So what I'm talking about when I talk about log parent functions are functions that look like y equals a log of any number base of x. Okay, so meaning there's no transformations here. Okay, so some examples might be y equals log base 2 of x, or y equals log base 3 of x, or y equals log base 1/4 of x, or y equals log of x, which of course is base 10, or y equals the natural log of x, which of course is base e. So those are all log parent functions. It's a log, any base you want, of x. Okay, so those are all log parent functions. I'll graph a couple here just to get you going on how to understand these graphs. The first one we will look at will be f of x, same thing as y, equals log base 2 of x. In fact, let's go ahead and just say y. Keep it simple here. Y equals log base 2 of x, and when you're setting up your table here, the x values that you want to plug in here are things that you can easily take a log base 2 of. And in this case, you want to put in powers of 2. 2 to the first, 2 squared, 2 to the third, 2 to the 0, etc. So I'll start with an x value of just 2. Then y would be log base 2 of 2. And I know that 2 to the first power equals 2, so this equals 1. If I put in 4 for x, I'll have log base 2 of 4, and I know that 2 to the second power is 4. If I put in 8, I've got log base 2 of 8, which is 3, because 2 to the third power is 8. Okay, and this of course can keep going on and on and on. Let's go the other direction though. Let's put in 1. What's log base 2 of 1? Well, 2 to the 0 power is 1. And then we need to put in all the reciprocals of these powers, so like 1/2 and 1/4 and 1/8, etc., etc., etc. Okay, so log base 2 of 1/2 is, well, 2 to the negative first power is 1/2. And log base 2 of 1/4 is negative 2, because 2 to the negative 2 is 1/4. And log base 2 of 1/8 is negative 3, etc., etc., etc. And if we plot these, we start to see something here. So I'm just going to roughly graph it. I always like to start with the middle here, the 1, 0. This point is kind of important because this is on every parent function. Every log parent function, the ordered pair 1, 0. And I always like to point out to my students anyway that the ordered pair 1, 0 looks like the letters L, O, which are the first two letters of log. Okay, so that helps students remember this sometimes. However, calculating the ordered pairs isn't that difficult if you understand logs. So I plot the ordered pair 1, 0 first, which is like right here. I'm not being terribly precise. And then I'll go down my list next, 2, 1. So I need to go right 2 units and up 1 unit, maybe like right there. Then 4, 2, so I go right 4 units and up 2 units, maybe right here. I need to go right 8 and up 3, so like this. And if I kept going, you would see that the graph as you move to the right is sort of flattening out. It keeps going up, but at a slower and slower rate. Okay, this is what students typically remember. Don't forget the rest of this. Okay, so I need all of this stuff. Don't forget. So if I plot 1/2 as my x, my y is -1. So 1/2 is right here, and I go down 1 unit. Then I go right 1/4 and down 2. So right 1/4 and down 2 puts me like here. Then I go right 1/8 and down 3. So that's even less to the right and down 3. And if you kept going, you know, these dots here indicate this pattern continues. You're going to keep getting closer and closer and closer to the y-axis, but you're never going to touch it. So your graph's going to do this sort of thing. It's going to curve down like this and keep getting infinitely close to the y-axis, but not touch it. And when you get infinitely close to a boundary like that, that boundary is called an asymptote. So you draw that with a dashed line to indicate that's your boundary, or asymptote is the technical term for it. Okay? So, since this is a parent function, I would usually like to write my asymptote over here with my ordered pairs. This vertical line crosses the x-axis at 0, so the equation of that vertical line is x equals 0. So my asymptote is x equals 0. In fact, every log parent function has this asymptote as well. Okay? So they all have the ordered pair 1, 0 in common. They all have the asymptote x equals 0 in common, because the graph gets infinitely close to the y-axis, or the line x equals 0. Let's do another one. We'll go through this one much quicker. Let me point out also that y equals log base 2 of x is the inverse of a function you may already know, the exponential function y equals 2 to the x. If you look at the ordered pairs for y equals log base 2 of x, they're all exact reverses of the ordered pairs of y equals 2 to the x. So if you forget how to come up with these ordered pairs, make your ordered pairs for y equals 2 to the x, and then inverse them to get the ordered pairs for y equals log base 2 of x. Log base 2 and a base of 2 are inverses anyway, okay? So I just wanted to throw that out there. Alright, let's do y equals log base 3 of x, and when we set up our table now, the x values that we're going to put in are going to be powers of 3. Okay, so I'll put in 1, 3, 9, 27, and then I'll put in those reciprocals, 1/3, 1/9, 1/27, and I could keep going in both directions if I wanted. I already know that if x is 1, y is 0, because I have log base 3 of 1, and 3 to the 0 power is 1. So that's that point we mentioned before that's always on the graph of a log parent function. Okay, log base 3 of the x value 3 is 1. Log base 3 of the x value 9 is 2. Log base 3 of the x value 27 is 3. And log base 3 of 1/3 is -1. Log base 3 of 1/9 is -2. Log base 3 of 1/27 is -3. And let's plot these again. I've got my 1, 0 here, the point that's common to every log function. Then I've got the ordered pair 3, 1, so I need to go right 3. So here's 1, 2, 3, and up 1. Then I need to go right 9 and up 2, 4, 5, 6, 7, 8, 9. I need to go up 2, so that puts me here. And then 27, 3 is way off the screen here. So you can see again, though, the general idea is the graph is flattening as I move to the right. It never gets flat, but it gets flatter and flatter. And again, don't forget this region down here. So I need to look at the order pairs on the top half of my table. If x is 1/3, which is like right here, y is -1. If x is 1/9, which is even smaller, I'm at -2. If x is 1/27, which is really close to the y-axis, I'm at -3. So again, my graph is getting infinitely close to my y-axis, so I need to draw in this dashed line because that's the line I'm getting infinitely close to, and that's my asymptote, x equals 0. Okay, so those are just a couple log parent functions, you should be able to graph them regardless of your base now. I did base 2 and base 3, but those could be 1/2 and 1/3 as bases even, it doesn't matter. The same ideas hold to calculate your ordered pairs, and you're always going to have this point and this asymptote, and your graph's going to flatten out in some direction and get infinitely close to the asymptote in the other direction. Okay, so those are your log parent functions.